Hey guys, so finally, it is only November, and we are finally into content that is absolutely not review. This stuff is definitely above Algebra 2's pay grade, and we are dealing with partial fractions. Now, I'm pretty stoked for partial fractions. I like them. I think they require some brain power to solve, in terms of figuring out the method anyway. Doing it just a bunch of procedural stuff, but the idea behind it's really cool. I think that the math involved is pretty varied. I think the problems can get very interesting, and they vary wildly based on what you're given. So let's go ahead and get into it. This is all we're doing today. I'm just kidding. Wait, there's more. So we're actually doing several different things today. Don't write all this down because we'll get to it. So we're going to go over the basics of partial fractions and their decomposition. And then we're going to decompose fractions with distinct linear factor denominators. So stuff like distinct linear factor denominators. So like x minus 2 times x plus 3. Those are distinct linear factor denominators because x minus 2 is a linear piece and x plus 3 is also linear. And then we're going to decompose fractions with repeated linear factor denominators. So something like a denominator of x minus 2 quantity squared, right? That's a repeated, because it's squared, linear factor denominator. Then we're going to decompose, well, actually, I don't think we're exactly in this order, but we'll get to all this. We'll decompose fractions with prime quadratic factor denominators. So stuff like this. A denominator like this. And then we'll do repeated versions of the same quadratic denominators. You might be thinking, oh my goodness, what did I just get into? Well, you got into Algebra 3, which you've been in this whole time, and now you're finally looking like we're doing some Algebra 3. And I just want to say, for the record, that every chapter going forward is going to have wildly new information. And this is just the tip of the iceberg. So on the last lesson, I made a stupid mistake at the end, which I will have put a annotation for on the video itself. But on the last example, we did a problem that resulted in this exact solution. If I can pull the problem up for a second, let's see if I can do that. So this says x plus 4 is equal to x plus 14 over x minus 4, x plus 2. All right, keep that in mind. So check this out. At the very end of this example, see, this is where I made the mistake. Check that out. It's x plus 2, x minus 4, x plus 2, x minus 4. Whoa, what happens here? Things magically change. This is supposed to stay x plus, and this is supposed to stay x. Regardless, whatever. Look at this. So we get x plus 14 over x plus 2, x minus 4. That's that right there, x plus 14, x minus 4, x plus 2. But we started with this, 3 over x minus 4 minus 2 over x plus 2, which is exactly this. Instead of starting here and working your way down to this answer, instead we are going to start here and work our way to here. And there's a good reason for this, but we won't get into specifically why we do this until later on. But the first thing I want to point out is that, or the thing I will say about it, is that in a lot of cases, you want to work with these partial fractions separately when doing more complicated math procedures to this. And it makes it easier to do certain things calculus based, which you're not in, but this is supposed to be preparing you for college level math, which is absolutely calculus. Anyway, so this idea of partial fractions is when you break a more complicated fraction into separate, simpler fractions. It is called partial fraction decomposition. So the practice of turning this fraction into these two fractions is called partial fraction decomposition. So when I mention partial fraction decomposition, this is what I mean. Each one of these fractions are called the partial fractions. Okay, so terminology. something to notice, and this is a really important thing to notice. The partial fraction numerators will always be 1 degree lower than the denominator. So if you look here, you have x to the first power, so it's a degree 1 polynomial. The numerator has no x's, aka x's to the 0 power. So if you look, 0 is 1 less than 1. That is very important. When we get on to the next part of this lesson, the second half, we're going to be dealing with denominators that are not degree 1. And in the numerator, we'll do things that are different. The idea is the numerator must always be 1 degree lower than the denominator. So keep that in mind. Now, how to decompose a fraction. This is the same example we saw earlier, but we're going to work it out, and I'll show it to you. So, first things first. And I am not, never mind. The first thing we want to do is break the denominator into break the denominator factors into their own fractions with unknown numerators. So we know we need to break this into partial fractions. And if you look here, the partial fractions share denominator pieces. So look, if the denominator is factored, the partial fractions will share those factors. So one partial fraction will have one of the factors, one partial fraction will have the other factor, right? This is always going to be the case. So here, we will separate this into 2 separate partial fractions. So that's the first thing. So partial fraction number 1, so x plus, actually let's not use this color, let's use this dark purple, I like it. X plus 14 over x minus 4, x plus 2. Actually, geez, this is not working out. I can do this again, if I can not be stupid. Okay. So I'm going to break this down into 2 separate partial fractions. And I know this will definitely be true. I know that one of the partial fractions will have this denominator piece, one of the partial fractions will have this denominator piece. That is all I can say for certain right now. The next idea that we have to start implementing is the idea of assigning variables to things we don't know. This method is very creative, and it involves really the essence of algebra, which is assigning variables to things we don't know, using logic to solve for those things that we don't know in a logically sound mathematical way. So we don't know what the numerator here is. We can make a claim about its denominator because it has to share factors with these denominators, but we don't know what the numerator is. We do know that it is 1 degree lower than the denominator. The denominator has a degree of 1. It's just simply x minus 4, x to the first power minus 4. So if you're in this situation, you always want to set the numerator to be a single number. And something I want to point out, I keep derailing myself, but I do it intentionally. This is the general form for a degree. This is probably important for you going forward. This is the general form for a degree 0 polynomial. It's just a. And where all these letters that are not x are constants. Okay, so that's a constant. So a degree 0 polynomial is just a number. A degree 1 polynomial is something like ax plus b, where it's got x to the first power, some coefficient in front of it, and then some other number at the end. This is a degree 1 polynomial in standard form. A degree 2 polynomial would be ax squared plus bx plus c. That's your degree 2 polynomial. And I'm sure you guys can imagine this expanding. A degree 3 polynomial would be ax cubed plus bx squared plus cx plus d. Right, there's your degree 3 polynomial. These standard forms are what we will be using for these numerators. If this is a degree 1 polynomial down here, we'll need a degree 0 polynomial here. And the general form or the standard form for that is just a letter, a, which represents a number, right? These represent numbers. So I will put a here, and I will put b here, because they're not necessarily the same thing, but they are both degree 0 polynomials. If you are confused right now, just for now, just say that our numerators are just going to be unknown numbers that we don't know yet. And I'm just giving them the labels A and B. Now, the next step is to eliminate the denominator by multiplying both sides by the denominator and of the main fraction, right? So here's your main fraction. If we multiply this fraction by the denominator, which is going to be x minus 4 times x plus 2, and then multiply each of these by x minus 4, x plus 2, and this one, x minus 4, x plus 2. Check out what happens. So remember, these are numerators. So look here. The x minus 4 and the x minus 4 cancel. The x plus 2 and the x plus 2 cancel. And you are left with x, hey, I said purple, x plus 14. This entire denominator canceled. Over here, the x minus 4 and the x minus 4 cancel, but the x plus 2 stays in the numerator. So you're going to have a times x plus 2. And then here with b, the x plus 2 and the x plus 2 cancel, but the x minus 4 stays. It does not cancel. So it stays in the numerator with b. So you're going to have plus b times x minus 4. This is where we're about to get to the point where this gets really clever. I don't want to make the same stupid mistake I made last lesson. So this is what we've done so far. What we want to do now is to distribute and simplify the partial fractions. So I want to distribute a into here and b into here. And man, what's about to happen is like, kudos to whoever discovered this, because it is awesome. All I'm doing right now is distributing. A times x is ax, a times 2 is 2a. B times x is bx, b times negative 4 is negative 4b. Now, the next step is to, and man, I left a lot of space here because this was like a smartboard exercise and I write bigger on the smartboard. So the next step is to group the terms to separate the x's from the constants. So I'm going to scroll back up and do that. Separate the x's from the constants. So if you look here, check this out, you've got an x here and an x here, but then you have a constant here and a constant here. Remember, a's and b's without x's are just numbers, they're constants. So we want to group these terms together. So we got x plus 14 is equal to ax plus bx plus 2a minus 4b. Oh man, here's where it's about to get exciting. Factor out x, then compare what we have to the numerator of the main fraction. And this is going to be the numerator of the main fraction, but we'll see here. Factor out x. So you're going to get, if you factor out x from here, these two pieces, you're going to have x times a plus b plus 2a minus 4b. And that's equal to x plus 14. This is where the magic happens. All right, this is where it all happens. This is what we're claiming, right? This is the claim that is being made. And it's important that you follow along like mentally here. There's an equal sign here. All right? These 2a and minus 4b is just a number. Just a number, all right? And then a plus b here is also just a number. But the equal sign is what's so important. If you look on the left side of the equal sign, how many x's do we have? You should say 1x, Mr. Dybel. It's just 1, right? If there's 1x on the left and we're saying it's equal to something, there's got to be 1x on the right. That is what's so clever about this. We have worked this problem out in such a way that we can make such simple deductions given the equation. If you look on the left, there's 1x. But on the right, it looks far more complicated. We have a plus b times x, right? Well, if I want to rewrite this, a plus b times x this way, we should be able to see that this is the number of x's that I have. If a plus b was 7, I would have 7 x's. If a plus b was 9, I would have 9 x's. But the equation, these sides being equal, says that my left side must be 1x. That means that a plus b, this piece right here, has to be 1. Super cool. Furthermore, the number by itself is 14. And remember, this is just a number. So this stuff right here has to equal 14. So we have to say that 2a minus 4b equals 14. Now we have a system of equations. So the next step is to make a system of equations based on what we know. This is best seen through an example. So I just explained this. We see that the number of x's we have on the right has to equal the number of x's we have on the left. And the number of x's we have on the left is 1x. So a plus b has to be 1. And then here, 2a minus 4b has to equal the number by itself, which is 14. And you get this set up here. And now you just solve this like a typical system. So I'm going to solve it like a typical system. Multiply this by negative 2 to cancel out the a's. So you get negative 2a minus 2b is equal to negative 2. So you get negative 6b is equal to 12. And so b is equal to negative 2. Now that I know b is negative 2, I'll plug that in right there. And I'll have a minus 2 equals 1. And so a is equal to 3. Finally, now that I know a and b, 3 and negative 2, I go all the way back to the beginning. In my partial fraction, I replace a with 3 and b with negative 2. And I get that, solve the system, write the completed partial fraction. The completed partial fraction was, man, look at all this scrolling. It's 3 over x minus 4. So 3 over x minus 4. 3 over x minus 4. And then it was plus negative 2 over x plus 2. Is that right? Scroll up, scroll up, scroll up. Yep. B over x plus 2. So b is negative 2. So negative 2 over x plus 2. This is your partial fraction decomposition. Hooray. 17 minutes in. But now that I've got the first bit out of the way, doing the rest of them should be easy. But I promise you, this is going to be a long lesson. You try and decompose this one. I know we're 17 minutes in, 18 minutes in, and we're like not even halfway done, but you need to give it a go. That's going to get harder. So if you don't have a solid footing now, it's going to be bad. So follow along what we did, try to mimic what we did above and work out your problem. I'm going to go ahead and assume that you already paused the video, you already tried it, and you got stuck somewhere, or you did it successfully, in which case, great, but I'm going to go ahead and work it out. First thing that we do is for factors that look like this, linear factors that are raised to the first power, you separate them into a over x minus 3 plus b over x plus 4. That's the first step. Each of these denominators becomes separate fractions, and the numerator is at 1 degree lower, degree 1, degree 0, so we're good. Next, we want to multiply both sides by the denominator over here. This is something that we need to shorten going forward. We can't afford to spend the time to do all this going forward. So if we multiply by x minus 3, x plus 4, and x minus 3, and x plus 4. If we do this, the x minus 3 here will cancel, the x plus 4 here will cancel, and then over here, the whole thing will cancel. So you're going to have, and I'm going to skip doing this in the future. My idea, what I think about in my head is, look, there are these pieces here, minus x minus 3 and x plus 4. A is going to gain the pieces that it does not have and lose the piece that it does have. If you look here, this canceling thing is always going to happen. It's always going to attach with the term that it did not have. This is something I'm going to skip in the future. If you look here, if you multiply this out, the x minus 3 and the x minus 3 will always end up canceling. This x plus 4 and this x plus 4 will always end up canceling. And it will gain the factor that it does not have. So right now it has an x minus 3. It's going to lose that and gain an x plus 4. Like this. I'm going to skip directly from this to this going forward. Actually, I'm going to go from here to here. So now you distribute. Now you combine your x terms. So we got the ax here and the bx here. And then you've got your 4a and your minus 3b. Now you factor out your x here. Now is when you make the comparison. We have 5 x's, so this is the number associated with how many x's we have on the left. So a plus b has to equal 5. And then here, we have negative 1 by itself, so this right here needs to be negative 1. 4a minus 3b needs to equal negative 1. And now you solve this system. I'm going to multiply this by 3, and I will get 3a plus 3b equals 15. And so 7a is equal to 14, and so a equals 2. Now that I know a, I'm going to take that and I'm just going to plug it back in right up here. And I'm going to get 2 plus b equals 5, and so b is equal to 3. And now that I know a and b, I will rewrite that right here. That I will get 2 over x minus 3 plus b over x plus 4, which is 3 over x plus 4. Boom, done with the problem. So that only took a couple of minutes. Once you get the hang of this, you'll be good. Moving on. Decomposing fractions with linear repeated factors. Now, this is almost identical to the step above, or to the stuff above, but there's one extra step. When you have a repeated factor, when you break down the main fraction, you need to include a term for each power of the repeated factor. When you break down the main fraction into this setup here, this one here, you will need a separate partial fraction for each power of the repeated factor. So let me explain, or let me break this down for you. So the x minus 18 over the x times x minus 3 quantity squared, this is the repeated factor. So when you break this down, you'll still have a piece with x because each piece needs to be reflected. Then you'll have 2 more pieces here. You'll have one piece, so this is to the second power, so you need one for each power. So you need a partial fraction with x minus 3 to the first power. Then you need another partial fraction with x minus 3 to the second power. This is the idea. Now, if you look at the actual factor, x, x minus 3, and x minus 3, those are all still linear. So the numerators of these partial fractions are still going to be degree 0 polynomials. So a, b, and c. Now we're going to solve this. And I'm going to go ahead and work all of this out right up here. I am going to multiply both sides by the entirety of this denominator. And I'll demonstrate what happens with this first one, and I'm going to skip it for the rest of them. Actually, I'll do it on this piece here. I'm going to multiply every term by this here. This denominator by every term. The more, like, you should try to start seeing it in a way that you don't have to write this out. So here, the x cancels, but you still have x minus 3 quantity squared. Here, one of the x minus 3's cancel, and you still have x and x minus 3. Here, both of the x minus 3's cancel, but you still have the x. And here, everything cancels. And so what you're left with is a times x minus 3 quantity squared plus b times x minus 3. And here you've got c times x is equal to x minus 18. Now, multiply everything out. So this is going to be a times, and now what I'm going to write here is so pay attention, I'm not going to write this down. What I'm about to write inside this set of parentheses is what you would get if you took x times 3 and squared it. Not x squared minus 3 squared, that's not what you do. It's x minus 3 times x minus 3 and FOIL that out. You're going to get x, I'm going to start treating you guys like your Algebra 3 students. So this would be x squared minus 6x plus 9 plus bx squared. Now I'm distributing in here. Bx squared minus 3bx plus cx equals x minus 18. Now I'm going to distribute the a into each piece here. And I'm going to get ax squared minus 6ax plus 9a plus bx squared minus 3bx plus cx equals x minus 18. Now I'm going to group my x squareds. So we've got an x squared here and an x squared here. And you've got ax squared plus bx squared. And then I'm going to group my x's next. So negative 6ax minus 3bx plus cx. Put that here. Coming up next, minus 6ax minus 3bx plus cx. And finally, your 9a. Man, moving on, moving good so far. We need more space. Hey, you. Hey, you. Get out of here, you. I need more space. Excuse me, pardon me, coming through. Coming through. I need more space. Oh, man. All right. More space acquired. Easy peasy. So, now that I've got my squareds together, my x's together, you want to factor them out. So factor out x squared, and you're going to get a plus b. That's what happens when you factor out x squared here. Factor out x here, not anything else, just x, and you're going to get negative 6a, and then minus 3b, and then plus c, and then you're going to have plus 9a. So if you just took away x, you'd have negative 6. Took away x, you'd have minus 3. Take away x, you'd have c. And this equals x minus 18. And here's where the magic happens. Now we're able to compare. This is the quantity of x squareds we have, this is the quantity of x's we have, and this is the quantity of number by itself, like constants we have. Do we have any x squareds over here? No, we don't. We have x minus 18. So I know that a plus b, since it's depicting the number of x squareds we have, has to be 0. Then I know that we have 1x, so this whole thing here has to be 1. Negative 6a minus 3b plus c equals 1. And then, see here. Give me just 1 second. Okay, we're doing good. It's we're at 30 minutes though, so So yeah, I guess that's a problem. Wait, where'd my mouse go? There it is. All right, so I have 4 monitors, so I mean, it's kind of difficult to find my mouse sometimes. And then here we've got 9a equaling negative 18 because this is the number by itself, this is the number by itself. So 9a has to equal negative 18. And now you solve this system. And it's actually not a hard system to solve because this third equation can be immediately solved for a. We can immediately say that a is equal to negative 2, right? Because you just divide both sides by 9 and you get a is negative 2. And this creates a chain reaction. Now that we know that a is negative 2, we can plug that in right here. And you get negative 2 plus b is equal to 0, and so b has to be 2. So b is 2. And now that we know a is negative 2 and b is positive 2, plug that in right here and find c. So you get negative 6 times a, which is negative 2, minus 3 times b, which is positive 2, plus c, which is 1, equals 1. And so you get 12 minus 6 plus c equals 1, so 6 plus c equals 1, so c equals negative 5. All right, now that we know a, b, and c, you go back up to the beginning here, you would go up here as your final answer. I don't have time to do this, but you would take your a, b, and your c, and you would write them here. So a is negative 2, a is negative 2, b is positive 2, and c is negative 5. And this right here, without the crosses through them, would be your answer. Negative 2 over x, 2 over x minus 3, and negative 5 over x minus 3 quantity squared. Okay. That is, man, we still have a little bit to do. So give me just a second, I need to change slides. Let me find it. Here it is. So another example, more stuff. Oh, that's not what I want. All right, so more stuff. Now we're going to decompose fractions with quadratic factors. And this is going to take at least another 10 minutes. Man. I guess we just have 2 examples to do. All right, so now that we have, look, this is the key difference. Boom. It's a squared factor. So not only do we have a factor here with 3 terms, but it is squared. So when setting up the partial fractions, the numerator for the quadratic piece of this one, the quadratic piece, so this is the quadratic piece, will be bx plus c, because that is the general form for a degree 1 polynomial. This is degree 2, right, squared. So the general form for the degree 1 polynomial is this, bx plus c. Because you could do ax plus b, but we'll already have used a, so you just move on to the next letters. B and c may change based on how many letters you've used already. The idea of the thing is still exactly the same, and we'll get to all that. So break down into partial fractions. You're going to have 2 partial fractions, because you've got 2 denominator pieces. One of them will be x minus 2, and one of them will be x squared plus 2x plus 4. The numerators are 1 degree lower. So this is a degree 1, so this is degree 0, a. This is degree 2, so this is degree 1, bx plus c. Now this is equal to the fraction up there, so 3x squared plus 17x plus 14 all over x minus 2, x squared plus 2x plus 4. The same steps apply though. So you want to multiply both sides by the entire denominator here. And when you do that, all right, this is what I was talking about earlier. If you multiply both sides by this entire denominator, the x minus 2 with the x minus 2 will cancel, and this piece will still remain on the a. So you'll get a times x squared plus 2x plus 4. Then here, when you multiply the denominator, this entire denominator here, the quadratic piece will cancel, but the x minus 2 piece will not cancel. Try to imagine that. And so you're going to have plus bx plus c times x minus 2. This is going to equal, because then both of these pieces will cancel, and you'll get 3x squared plus 17x plus 14. And now you work through all this. Multiply everything out. combine your x squareds, combine your x's, combine your numbers, factor out your x squareds, factor out your x's, and then compare. It's a really cool process. I think it's pretty detailed, and it's starting to get into the more complicated mathematics. So I'm just writing all my arrows for distributing. Ax squared plus 2ax plus 4a plus bx squared minus 2bx plus cx minus 2c equals 3x squared plus 17x plus 14. Boom. So this piece was spread out here, and this piece was spread out here. Now you combine all your squared pieces, these two pieces. Combine all of your regular x's. And then combine all of your numbers by themselves. And then it equals the same thing it equaled earlier. Wait. Okay. And so now you factor out your x's and your x squareds. You get 2a minus 2b plus c, and then you keep these by themselves. And then you compare. And now you compare. So how many x squareds do you have? Well, you have 3. So the idea here is you have 3x squareds, so this has to equal 3. You have 17 x's, so this has to equal 17. And you have 14, so these have to equal 14. So a plus b equals 3. 2a minus 2b plus c has to equal 17. And then 4a minus 2c equals 14. I'm going to set this up into a matrix equation and solve it. So the matrix equation, it's going to have it's going to be a 3 by 3. And the order of my variables will be a, b, c. And it's going to equal 3, 17, and 14. And so you're going to put in your coefficients here for a, b, and c in your first, second, and third equations. So you've got 1a in your first equation, 1b in your first equation, and then 0 c's, because you don't see a c here, right? Then here you've got 2, negative 2, 1. And here you've got 4 a's, 0 b's, and negative 2 c's. Do this on your calculator, and you should get... What should you get here? You should get 5, negative 2, 3. So you should get that a equals 5, b equals negative 2, and c equals 3. Do this on your calculator. Set this up as matrix A, set this up as matrix B, and then do A inverse B. And you should get 5, negative 2, 3. And so you work out the problem you finish the problem by writing out this partial fraction decomposition where you replace a, b, and c. So instead of a over x minus 2, you've got 5 over x minus 2. And then instead of bx plus c, you're going to have negative 2x plus 3 over x squared plus, was it 2x plus 4? Yeah. There is your partial fraction decomposition. Finally, decomposing fractions with repeated quadratic factors. Notice, look at that, it's quadratic. It's squared, but it's also the entire factor is squared. So if you remember last time we were dealing with repeated factors, you need a partial fraction for each power of the factor. So we'll need one of these to the first power, and we'll need another one to the second power. And that's the only factor down here, so that's all we have to worry about. So you're going to have x squared plus 1. When you're doing your decomposition, your pieces are going to be x squared plus 1 to the first power and x squared plus 1 to the second power. And then 1 degree lower, it's a degree 2 down here. So you need a degree 1. So ax plus b and cx plus d. It needs, since the denominator is degree 2, so it has an x squared, your numerator needs to have an x to the first power, and this is how you set that up. Now I'm going to go ahead and jump right into the steps. You're going to be multiplying each of these terms, and this thing equals this, right? But when you multiply each term by x squared plus 1 quantity squared, they'll both cancel out in this case. When you multiply this by it as well, one of them will cancel out in this case. And you'll be left with still, let me just write this out. One of them will cancel here, but you'll still have one left. And in this case, both of them will cancel. So you will have ax plus b times this x squared plus 1 plus cx plus d times nothing equals the numerator, 5x to the third minus 3x squared plus 7x minus 3. And you're going to have to distribute, and you're going to get ax to the third plus ax plus bx squared plus b plus cx plus d equals this whole thing. Combine all of your x's to the appropriate powers together. We only have 1x cubed, we only have 1x squared. We have 2x terms, so they combined here. And then your b and your d combine as well at the end here. And that still equals the same thing. So factor out your x. So if you look here, you have a x cubes, b x squareds, a plus c x's, and b plus d numbers. So these are the things you're comparing to. So he says a x cubed, that has to be 5. So a has to be 5. Well, that's convenient. Here, you've got b x squareds, so b has to be negative 3. And here, the number of x's you have is a plus c x's. So a plus c has to equal 7. And here you've got b plus d, which has to equal negative 3. And this is just a simple plug in what you know. A is 5, so I'm going to plug that in right here. And b is negative 3, so I'm going to plug that in right there. So you're going to get 5 plus c is 7, so c is equal to 2. And then negative 3 plus d is equal to negative 3, so d has got to be 0. So the answer is this partial fraction written with all of these in it. So you're going to have ax plus b, so 5x minus 3 over x squared plus 1, plus cx plus d over this piece, so 2x plus 0 over x squared plus 1 quantity squared. Man, 43 minutes. Holy crap. There's your homework. This will take quite some time to finish compared to other homework assignments. Make use of your time wisely. You're going to have a quiz soon, and man, you had better start reviewing for it because there's a lot of problems to do, and you will have an entire day in class to work on stuff over it. So make sure you take advantage of it. Ask me if you need help. This took a long time to teach, so try to wrap your brain around it.